Hello dear students, in this video we will continue with the revision for CBSE board examination. In this video we will have a recap of the concepts from the second chapter, which is algebra. The second chapter, algebra, consists of two major topics. One is matrix and the other one is determinants. First we will see the definition of matrix. It is a rectangular array or table of numbers, symbols, expressions or functions, which is arranged in the form of rows and columns. Each member in a matrix or in this arrangement, it is called an element of the matrix. So this is with respect to the definition of matrix. And next we will see the order of matrix. The order of a matrix, if we have a matrix A of this form, that is, if we see this matrix A, it has m rows and n columns. So if a matrix A has m rows and n columns, then the expression which is given by m by n, it is called the order of this given matrix A, where I varies from 1 to m and j varies from 1 to n, where this I and j belongs to the set n of natural numbers, and we read this expression as m by n. This is called the order of a matrix. The elements A11, A12, A13 up to etc., all these are nothing but the elements of this matrix A. So if we consider these elements A11, A22, A33, where we have Aij for all I equal to j, then these elements are called the elements of the diagonal or diagonal elements of the matrix. It is called diagonal elements of the matrix. And all the other elements apart from this diagonal elements, they are called the elements of non-diagonal or non-diagonal elements of matrix A. So this is with respect to definition of matrix, order of a matrix, the elements in the diagonal and the non-diagonal elements. Now we'll see an example. The first example in handbook. Shalab has 3 books, 2 pens and 3 notebooks, while Reshmi has 1 pen, 4 books and 5 notebooks in their respective school bags. Express this information as a matrix and what is the order of the matrix obtained. So here we have the two students and the items they have in their respective school bags are given. We have to express this information as a matrix, and we should also write the order of the matrix. So here first let us represent the given information in the question in a tabular form. We have two students, Shalab and Reshmi, and they have books, pens and notebooks. Shalab has 3 books, 2 pens and 3 notebooks. Reshmi has 4 books, 1 pen and 5 notebooks. We can represent this in the matrix form as 3, 2, 3 and 4, 1, 5. The rows represent the students and the column represent the items they have in their respective school bags. So here the order of this matrix, it has 2 rows and 3 columns. So it is 2 by 3. And the next example, write the coordinates of triangle ABC with vertices A 4, -1, B 3, 2 and C 2, -4 in a matrix formation. So here the vertices of triangle ABC, it can be written in the matrix form as in 2 ways. So we can have x is equal to, here we can have the vertices in the rows and the coordinates in the columns. So here we can have 4, -1, 3, -3, 2, then 2, -4. The order of this matrix, it is 3 by 2, or we can have it as y is equal to the vertices of A, it is 4, -1, B, it is 3, 2 and C, it is 2, -4. So we can express this in either of these 2 ways. The order of this is 2 by 3. So this is how we can represent the vertices in the matrix form. Next question, if a matrix has 4 elements, what are the possible orders such a matrix can have? So if a matrix has order m by n, it means it can have m into n elements. In a matrix of order m by n, we have m into n number of elements. So if a matrix has 4 elements, the various possible orders are the number of ordered pairs which can be formed by the factors of 4. So we can have 4 as 1 into 4, 4 into 1 and 2 into 2. So we can have the various orders for this matrix as 1 by 4, 4 by 1 and 2 by 2. So these are the possible orders. Next question, construct a 3 by 3 matrix whose elements are given by Aij equal to I plus 2j by 5. So here let us take, let the matrix be, let us express it in the general form given by A11, A12, A13. It is a 3 by 3 matrix, so it should have 3 rows and 3 columns. Then next row will be A21, A22, A23. The third row will be A31, A31, A32 and A33. So now we can find each of the elements by substituting for I and j. So A11 will be 1 plus 2 by 5. Here we are substituting I as 1 and j as 1. So 1 plus 2 by 5, it is 3 by 5. Then A12 will be 1 plus 2 into 2 by 5. It is 5 by 5, which is 1. Then A13 will be 1 plus 2 into 3 by 5, which is 7 by 5. Then A21 will be 2 plus 2 into 1 by 5, which is 4 by 5. Then for element A2, we have 2 plus 2 into 2 by 5, which is 6 by 5. Then for A23, it is 2 plus 2 into 3 by 5, which is 8 by 5. Next we have the elements of the third row, A31. So it is 3 plus 2 into 1 by 5, which is 5 by 5, 1. Then the value for the next element is A32 is 3 plus 2 into 2 by 5, which is 7 by 5. The last element A33, it is 3 plus 2 into 3 by 5. It is 9 by 5. So the required elements of this matrix are given by 3 by 5, 1, 7 by 5, 4 by 5, 6 by 5, 8 by 5, then 1, then 7 by 5 and 9 by 5. So this is the required matrix whose elements are given by Aij equal to I plus 2j by 5. Since it is a 3 by 3 matrix, we started with writing it in the general form with 3 rows and 3 columns. Next we have the different types of matrices. The first one is rectangular matrix. We call a matrix a rectangular matrix if the number of rows is not equal to the number of columns. So it is in the form of a rectangle. See here, if we have a matrix of order this 3 by 2 with 3 rows and 2 columns, then it is an example of a rectangular matrix. The next matrix is a square matrix, a matrix in which the number of rows is equal to the number of columns, then such a matrix is called a square matrix. So here if we see this matrix B, it has equal number of rows and columns. It is a square matrix of order 3 by 3, or we can simply say B is a square matrix of order 3. Here the number of rows are equal to the number of columns. And next we have the next type of matrix, which is the row matrix. If a matrix has only one row, then it is called a row matrix. Say for example, this matrix D, it is a row matrix of order 1 by 2. So If we have n elements in a row matrix, then the order is given by 1 by n. Next we have the next type, which is column matrix. A matrix which is having only one column for given number of rows. It is called a column matrix. So here if we consider this matrix C, it is a column matrix of order 3 by 1. It has 3 rows and 1 columns. So for a given number of rows m, then the column matrix is given by m by 1. Next we have the diagonal matrix. Here we call a matrix a diagonal matrix if it is a square matrix and it has all non-diagonal entries as 0. Then such a matrix is called a diagonal matrix. That is, only the elements on the diagonal will be non-zero. The other elements will be 0. So this is an example. These are examples of diagonal matrix. So here this is a diagonal matrix of order 2 and this is a diagonal matrix of order 3. And next we have the next type of matrix, which is the scalar matrix. We call a matrix a scalar matrix if it is a diagonal matrix and it has the same diagonal elements. Then such a matrix is called a scalar matrix. Say for example, R is equal to 5 0 0 5. Then such a matrix, it is called a scalar matrix. The next matrix is the identity matrix. An identity matrix, it is a scalar matrix in which the diagonal elements or the diagonal entries are all equal to 1. So here Aij equal to 1 for all I equal to j and Aij equal to 0 for all I not equal to j. So the diagonal elements are 1, the other elements are 0. Such a matrix is called identity matrix. It is denoted by capital letter I. It is also known as the unit matrix. So if we have a unit matrix of order n, it is written as In. So here if we consider this first identity matrix of order 1, then it is a unit matrix of order 1. This is a unit matrix of order 2. This is a unit matrix of order 3. Next one is the zero matrix. If a matrix has all elements 0, then such a matrix is called zero matrix. So here a scalar matrix with 1 as each diagonal element is an identity matrix. And next we have equal matrices. We say two matrices A and B having same order m by n as equal matrices if each element of A is equal to the corresponding element of B. That is, Aij equal to Bij for all 1 less than or equal to I less than or equal to m and 1 less than or equal to j less than or equal to n. We denote the equal matrices as A equal to B. So we have 1, 2, 5, 7 if this is matrix A, and if this is equal to another matrix B, A, B, C, D, then each element of matrix A will be equal to the corresponding element of matrix B. So we will have A equal to 1, B equal to 2, C equal to 5 and D equal to 7. So this is with respect to different types of matrices. Now we will continue with some of the examples. If A equal to 1, 2A minus 8, B plus 1 and B equal to 1 minus 6 minus 8, 13 are equal matrices, find the values of A and B. So here it is said A is equal to B. We have to find the values of A and B. Given A equal to B, that is 1, 2A minus 8, B plus 1. This is equal to 1 minus 6 minus 8, 13. So the meaning is that each element of A is equal to the corresponding element of B. So we can compare the terms in these two matrices. So on comparing, we have 2a equal to minus 6. 2a equal to minus 6 implies a equal to minus 6 by 2, which is minus 3. Then b plus 1 equal to 13. b plus 1 equal to 13 implies b equal to 12. So these are the values of a and b. Next we have find the values of a, b, c and d from the following equation. So here it is given these two matrices are equal. So again we can compare the terms. So comparing 2a plus b equal to 4, a minus 2b equal to minus 3, then 4c plus 3d equal to 24. Then 5c minus d equal to 11. So here each term are equal to the corresponding term in the other matrix. Now we can solve these two equations and find a and b. Solve these two equations and find c and d. So here if we multiply this equation by 2, we get 4a plus 2b equal to 8. And here a minus 2b equal to minus 3. When we add, we get 5a equal to 5, implies a equal to 1. Now when we put a as 1 in this equation, we get b as 2. Then here we can multiply this equation by 3. So we get 15c minus 3d equal to 33. This is 4c plus 3d equal to 24. So if we add these two, this will cancel. We will get 19c equal to 57 or c equal to 57 by 19, which is 3. When we substitute c as 3 here, we will get d is 15 minus 11, which is 4. Therefore, we have a equal to 1, b equal to 2, c equal to 3 and d equal to 4. So these are the values for a, b, c and d. Now let us move on to the next topic, which is algebra of matrices. So the first topic is multiplication of a matrix by a scalar value. If we have a matrix A equal to Aij of order m by n, and if k is any scalar quantity, then we can find k into A as another matrix, which is obtained by multiplying each element of this matrix A by the scalar quantity k. So Ka equal to k into this matrix Aij. It is nothing but the matrix Kaij, where I varies from 1 to m and j varies from 1 to n. The order of this new matrix will be the same as the order of the original matrix. Next we have the properties of scalar multiplication. If we have two matrices A equal to Aij and B equal to Bij of same order, say m by n, and if k and p are two scalars, then we have these properties holding true. K into A plus B equal to Ka plus Kb, then K plus P into A will be equal to Ka plus Pa, and K into A minus B equal to Ka minus Kb. So these are the properties of scalar multiplication. Now continuing with algebra of matrices, the next one is addition of matrices. If we have two matrices A and B of the same order m by n, then the sum of two matrices A and B is defined, and we obtain a new matrix S given by A plus B equal to matrix Sij of order m by n, such that Sij equal to Aij plus Bij. So the elements in the new matrix will be the sum of the corresponding elements of A and B, where I varies from 1 to m and j varies from 1 to n. Now we have the properties of addition of matrices. We say addition of two or more matrices is possible only when the given matrices are of the same order, and the order of the resulting matrix will also have the same order as the given matrices. Then the next property is matrix addition is commutative. That is A plus B is equal to B plus A. And next matrix addition is associative. That is A plus B plus C. If we add B plus C first and then if we add A to it, this will be equal to the sum of A and B and then adding C. So it is associative. Then the next property is zero matrix is the additive identity. That is, if we add the identity matrix to any matrix, we will get the same matrix. So matrix A plus the zero matrix, it is equal to A. It is equal to zero matrix plus A. And then negative of a matrix, it is the additive inverse of the given matrix. So if we have a matrix A of order m by n, then the additive inverse of A, it is negative A. It is the matrix negative of A of order m by n. So when we add the given matrix and the additive inverse of this matrix, we will obtain the zero matrix. So that is the meaning of this. Next we have subtraction of matrices. For two matrices A equal to Aij and B equal to Bij of same order m by n, then the difference of two matrices A and B is defined as a new matrix D given by A minus D equal to matrix Dij of the same order m by n, such that Dij it is equal to Aij minus Bij. The elements in the new matrix Dij is obtained by subtracting each element of B from the corresponding element of A, where I varies from 1 to m and j varies from 1 to n. So this is with respect to some of the algebra of matrices. Next we have negative matrix. So if we have a non-zero matrix A of order m by n, then a matrix B of the same order, it is called the negative matrix of matrix A if A plus B is equal to the zero matrix, and we denote the negative matrix A as negative of A. So the additive inverse of A, another name is, it is the negative matrix of A. Now we will continue with some of the examples. For matrices A given by this matrix, B given by this matrix and C given by this matrix, we have to calculate these. 2A, then A plus B minus C, then 3B minus A plus 2C. So the first one is 2A, it is 2 times the matrix A. So 2 into 3, 4, 0, minus 1, 12, 3, 6, 1, 2. So this is, we have to multiply each of these elements by 2. So it is 6, 8, 0, minus 2, 24, 6, 12, 2, 4. Then the next subdivision is A plus B minus C. So it is the sum of these two minus this matrix. So here we can see that all matrices are of the same order. So we can find A plus B minus C. It is defined. The order is defined. So here we have 3, 4, 0, minus 1, 12, 3, 6, 1, 2. Plus B is 7, 7, 2, minus 11, 0, 2, 3, minus 1, 4. Minus the matrix C. So this is matrix C. So A plus B minus C, it is equal to, so here it is 3 plus 11 minus 3 plus 7 minus 11. So it is 3 plus 7 minus 11, then 4 plus 7 minus 2, then 0 plus 2 minus of minus 3 plus 3, then it is minus 1 minus 11 minus 2, then it is 12 plus 0 minus 0, then it is 3 plus 2 minus 1, and next we have 6 plus 3 minus 1, 1 minus 1 minus 9, then it is 2 plus 4 minus 1. So this, when we simplify, it is minus 1 9 5, and then minus 14 12 4, then 8 minus 9 and 5. So this is the matrix A plus B minus C. Then we have the next matrix 3B minus A plus 2C. So the third subdivision, it is 3B minus A plus 2C. So it is 3 into matrix B, 7 7 2 minus 11 0 2, 3 minus 1 4. Minus A is the matrix A itself. Next we have plus 2C. 11 2 minus 3 2 0 1 1 9 1. So this is 21 minus 3 plus 22. Next we have 21 minus 4 plus 4. Next we have 6 minus 0 minus 6. Then minus 33 plus 1 plus 4. Then 0 minus 12 plus 0. Then 6 minus 3 plus 2. Then 9 minus 6 plus 2. Then minus 3 minus 1 plus 18. Then it is 12 minus 2 plus 2. So this, when we simplify, it is 40, then 21, then 0, and here it is minus 28, here minus 12, then it is 5, here again 5, next 14 and 12. So this is the matrix 3B minus A plus 2C. Next we have the next example. If x is minus 1 3 8 4 and y is this matrix, we have to find the matrix Z such that 2x plus y equal to 5z. So here if we have to have 2x plus y equal to 5z, then the order of z should be equal to the order of x and y. So here let us take, let z is equal to the matrix A, B, C and D. So 2x plus y equal to 5z, it implies 2 into the matrix X plus y. This is equal to 5 into matrix Z. So this is minus 2 minus 5 minus 7, then 6 plus 1 7. Here it is 2 into 8 16 minus 1 15, and here it is 2 into 4 8 minus 2 6. This is equal to 5 into A, B, C, D. Or this matrix A, B, C, D, it will be 1 by 5 into this matrix. This implies minus 7 by 5, 7 by 5, 3, 6 by 5. This is equal to the matrix Z. So this is the required matrix. Next question, find x and y. If x plus y is this matrix minus 1, 13, 2 and 4, and x minus y is this matrix 5 minus 3, 3 and 5 minus 8, 3 and 0. So if we have x plus y as this matrix and x minus y as this matrix, we have x plus y plus x minus y. It will be the sum of these two matrices. Plus 5 minus 8, 3, 0. So here we have y minus y. Y minus y is 0 matrix. And then we have x plus x. It is 1 into x plus 1 into x. So it is 2x. And here y minus y is the 0 matrix. So 2x plus the 0 matrix is 2x itself. So from here we have 2x as the sum of these two matrices. So minus 1 plus 5, 4. Then 13 minus 8, 5. 2 plus 3, 5. 4 plus 0, 4. So from here we have x as 2, 5 by 2, 5 by 2, 4. I'm sorry, 5 by 2, 2. So this is x. Next we can find y. If we subtract these two, x plus y minus of x minus y, it will be the difference of these two matrices. Minus 5 minus 8, 3, 0. So here again we will have x minus x, which is the 0 matrix, then plus y. Here minus of minus y will be plus y. So this will be 2y. So the left hand side will be 2y. This implies 2y equal to the difference of these two. Minus 1 minus 5 minus 6. Next 13 minus of minus 8 is 13 plus 8, 21. 2 minus 3 minus 1, 4 minus 0, 4. So y will be, we have to divide each of this term by 2. So it is minus 3, then 21 by 2, then minus half and 2. So these are the matrices x and y. Now let us continue with the algebra of matrices. Next we have multiplication of matrices. For two matrix A equal to Aij of order m by n and B equal to Bjk of order n by p, the multiplication of matrices AB, it is defined as matrix P equal to A into B given by matrix Pik of order m by p, such that for finding the element Pik, we multiply ith row of first matrix A with the kth column of second matrix B and calculate the sum of these products. So here we can find the product of two matrices A and B only when the number of columns of A, it is equal to the number of rows of B. And after that we multiply ith row of A with kth column of B and add those products to obtain the first element. To obtain the ikth element of matrix P. Next we have the properties of matrices. Similar to addition of matrices, multiplication of matrices is also associative. That is AB into C, it is equal to A into BC provided the order of multiplication is defined on both sides. And next we have the distributive property, that is A into B plus C, it is equal to AB plus AC, and A into B minus C, it is equal to AB minus AC. And next we have the multiplicative identity matrix. So if we have a square matrix A of order m by m, then there exists multiplicative identity matrix I of the same order such that I into A equal to A into I equal to A. So this is with respect to properties of multiplication of matrices. Now we'll continue with examples. For A equal to this matrix 2, 3, 1, 2, prove that A square minus 4A plus I equal to O, where this O it is the 0 matrix. So first let us find A square. A square it is nothing but it is A into A. So this is 2, 3, 1, 2 into 2, 3, 1, 2. So here we have to multiply the elements of first row with the elements of the first column and add those products. So it is 2 into 2 plus 3 into 1. This is the first element. The next element is 2 into 3, the first row and the second column, plus 3 into 2. And next we have 1 into 2 plus 2 into 1. Next we have 1 into 3 plus 2 into 2. So this is 4 plus 3 is 7, and then it is 6 plus 6 12, 2 plus 2 4, and 3 plus 4 7. So we have A square minus 4A plus I. We have to prove that this is equal to 0. A square minus 4A plus I, it is equal to A square is 7 12 4 7 minus 4A is 4 into 2 3 1 2 plus I is the identity matrix. Here since the order should be defined, we need to have an identity matrix of order 2. 1 0 0 1. So this is 7 minus 8 plus 1, then 12 minus 12 plus 0, then 4 minus 4 plus 0, then 7 minus 8 plus 1. So it is 0 0 0 0, which is the 0 matrix. So this is what we have to prove, and we have proved. This is equal to RHS. Next question, given that X is a matrix of order 2 by n, Y is a matrix of order 3 by k, Z is a matrix of order 2 by p, W is a matrix of order n by 3, and P is a matrix of order p by k. What are the conditions? The first subdivision for n, k, p so that 3 py plus 2 wy is defined. So let us solve the first subdivision first. The first one is, that is this 3 py it should be defined. So for py should be defined, the number of columns in P, it should be equal to the number of rows of Y. So here we need to have k equal to 3. So order of py is, here we need to have k equal to 3. This will be p by k. And then we have wy. Order of wy will be, order of w is n by 3. So order of wy will be n by k. So for 3 py plus 2 wy to be defined, we need to have order of py equal to order of wy, or we should have p equal to n. So this is the condition for n, k and p, so that 3 py plus 2 wy is defined. K should be equal to 3. Next we have the second subdivision. For the second subdivision, For the order of matrix, 2x minus 3z to be defined, the order of x and z should be same. So order of x is 2 by n and order of z is 2 by p. So 2 by n should be equal to 2 by p, implies n equal to p. So these are the required conditions. Next we move on to some of the special matrices. The first one is transpose of a matrix. If we have a matrix A equal to Aij of order m by n, then the matrix obtained by interchanging the rows and columns of A, it is called transpose of A. And the order of transpose of A, it will be n by m. Here are some of the properties of transpose of a matrix. If we have two matrices A and B, A transpose the whole transpose, it is equal to A. Then Ka the whole transpose will be equal to K into A transpose, where A is any constant. Then A plus B the whole transpose is A transpose plus B transpose. And AB the whole transpose is B transpose into A transpose. So these are the properties of transpose of a matrix. Next we have the next example. If A equal to this matrix and B equal to this matrix, we have to find the matrix A transpose minus 2B. So here A transpose, it is obtained by interchanging the rows and columns of A. So the first row becomes the first column and the second row becomes the second column. So A transpose minus 2B, it will be 2, 1, 3 minus 4 minus 2 into B, minus 2, 3, 5 minus 4. So this is 2 minus of minus 4, it is plus 4. So 2 plus 4, 6. Then 1 minus 6 minus 5. Then 3 minus 10 minus 7. Then minus 4 plus 8, it is 4. So this is the matrix A transpose minus 2B. Next we have the symmetric and skew symmetric matrices. For a given square matrix A equal to Aij, if A transpose equal to A for I varying from 1 to m and j varying from 1 to n, then we call the given matrix A as a symmetric matrix. Say for example, if we consider this matrix root 3 minus 8 minus 8 9, here if we see the transpose of this matrix, it will be equal to matrix P itself. So this is a symmetric matrix because P transpose is equal to P. And next we have a skew symmetric matrix. For a given matrix A equal to Aij, if A transpose equal to negative A for all I varying from 1 to m and j varying from 1 to n, then A is called a skew symmetric matrix. One property of skew symmetric matrix is that all the diagonal elements are 0. Say for example, if we consider this matrix B, 0, minus 8, 8, 0, then the transpose of this matrix, it is the negative of matrix B. So B transpose will be 0, 8, minus 8, 0, which is minus B. So we call B as a skew symmetric matrix. And next we have the next example. If A, B are symmetric matrices of same order, then what can be said for matrix AB minus BA? So here it is given A and B are symmetric matrices of same order. Since A and B are symmetric matrices, implies A equal to A transpose and B equal to B transpose. Now AB minus BA the whole transpose, it will be AB the whole transpose minus BA the whole transpose. So this is AB the whole transpose by the properties of transpose of a matrix, it is equal to B transpose minus A transpose, and BA the whole transpose will be A transpose B transpose. Now here, since A and B are symmetric matrices, we have A equal to A transpose and B equal to B transpose. So in place of B transpose we can write B, and in place of A transpose we can write A. So this becomes BA minus AB, or if we take the negative sign outside, we will have it as AB minus BA. So we considered AB minus BA the whole transpose, and we got this equal to negative of AB minus BA. So if we have seen, if A transpose equal to negative A, then A is skew symmetric. So this implies AB minus BA is skew symmetric. So it is skew symmetric. And next we have, if A is a square matrix having real values as elements, then we can see that A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. So we can express any square matrix A as sum of symmetric matrix and a skew symmetric matrix. So if we consider A as equal to half of A plus A transpose plus half of A minus A transpose. If we add this, we will get it as half of A plus A is 2A plus A transpose minus A transpose will be 0. It is equal to A. So here we can express this A as half of A plus A transpose plus half of A minus A transpose, where A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. So we can express any square matrix A as a sum of symmetric and skew symmetric matrix. So here is an example. Express the matrix A equal to this matrix as a sum of symmetric and a skew symmetric matrix. So here this is A. So A transpose will be, the rows becomes columns. So it is 1, 2, 3, minus 4, minus 1, 0, 3, 5, 1. So let us take, let P equal to half of A plus A transpose. So it is half of A is 1, 2, 3, minus 4, minus 1, 0, 3, 5, 1, plus this half is outside. A transpose is 1, minus 4, 3, 2, minus 1, 5, 3, 0, 1. So this is half of the matrix 2, 1 plus 1 is 2, 2 minus 4 is minus 4, 3 plus 3 is 6, then minus 4 plus 2, minus 2, minus 1, minus 1, minus 2, 0 plus 5, 5, then 3 plus 3 is 6, 5 plus 0, 5, 1 plus 1, 2. So this is 1, minus 1, 3, minus 1, minus 1, 5 by 2, then 3, 5 by 2, 1. So here this we can see that it is a symmetric matrix. So P transpose will be 1, minus 1, 3, minus 1, minus 1, 5 by 2, then 3, 5 by 2, 1. It is equal to P, implies P is symmetric. Similarly, let us have Q as half of A minus A transpose. So it is half of 1, 2, 3, minus 4, minus 1, 0, 3, 5, 1 minus A transpose. 2 minus 1 5 3 0 1. So this is half of 1 minus 1 0, 2 minus of minus 4 is 6, 3 minus 3 0, then minus 4 minus 2 minus 6, minus 1 plus 1 0, 0 minus 5 minus 5, 3 minus 3 0, 5 minus 0 5, 1 minus 1 0. So Q will be 0 3 0 minus 3 0 minus 5 by 2 0 5 by 2 0. Now Q transpose, it will be 0 3 0. The first row will become the first column, the second row becomes the second column, and the third row becomes the third column. So this is equal to minus Q, which implies Q is skew symmetric. So we can express A as sum of P and Q, where P is a symmetric matrix and Q is a skew symmetric matrix. Therefore, A equal to P plus Q implies A equal to, this is the symmetric matrix. P is 1 minus 1 3, minus 1 minus 1 5 by 2, 3 5 by 2 1, plus the skew symmetric matrix Q. 0 3 0, minus 3 0 minus 5 by 2, 0 5 by 2 0. So if we add these two, we will get A. So this is how we can express a square matrix as a sum of symmetric and skew symmetric matrix. Now we have the next topic in algebra, which is determinant. Now we will see the definition of determinant. Every square matrix is associated with a number C, which is a real number or a complex number. It is called determinant of matrix A, and it is denoted by DETA or with this symbol determinant of A, or sometimes it is expressed as this Greek symbol delta, which also means the value of determinant. So we are familiar with calculating the value of the determinant. So here is an example. Given A equal to this matrix and B equal to this matrix, we have to find the values of each of these. The first one is we have to find the determinant of A. It is determinant of 3, 5, minus 4, 6. So we multiply these two minus multiply these two. So it is 18 minus of minus 20. 18 plus 20, which is 38. Then we have determinant of B. It is determinant of minus 9 to 1 minus 7. It is, we multiply these two minus multiply these two. So it is minus 9 into minus 7, which is 63. Minus 2 into 1 is 2. It is 61. Then we have the third subdivision, 2 into determinant of A. So it is 2 into 38, which is 76. And then the fourth subdivision, we have determinant of 2A. So it is determinant of the matrix 2 into A. So it is determinant of 6, 10, minus 8, 12. So we have to first find the matrix 2A, and then we find the determinant of that matrix. We find the determinant of 2A as 2 into matrix A, and then find the determinant. 2 into matrix A is this matrix. The corresponding value of determinant is given by 6 into 12 minus 10 into minus 8. So it is 72 minus of minus 80. So it is 72 plus 80. which is 152. Moving on to the next subdivision, determinant of A into determinant of B. So here we already got the value for determinant of A and determinant of B. So it is determinant of 3, 5, minus 4, 6 into determinant of minus 9, 2, 1, minus 7. We got these values already. This is 38 into 61. So it is 38 into 61, which is 2318. Now let us find determinant of A into B. So to find the determinant of A into B, first we have to find the matrix AB. The sixth subdivision, determinant of AB. So first we have to find the product of matrices A and B. This is A into B. So here to find product AB, we multiply first row, first column and add the numbers. So 3 into minus 9 minus 27 plus 5. So it is minus 22. Next we have 3 into 2, 6 minus 35. So minus 29. Next we have minus 4 into minus 9, 36 minus plus 6. It is 42. And next we have minus 4 into 2 minus 8 minus 42 minus 50. And now we have determinant of AB. It is equal to determinant of minus 22 minus 29, 42 minus 50. So this is minus 22 into minus 50 minus of minus 29 into 42. So it is minus 22 into minus 29 into 42. So this when we simplify, again we will get it as 2318. So these two are equal. Next question, find x if determinant of this is equal to determinant of this. So this is not like matrix, we cannot compare the terms. Here this is a real or complex number and this is a real or complex number. So here we are given 3 minus 6, 4, 0. This is equal to 3x square x minus 1. So here the value was 0 plus 24 and here the value was minus 3 minus x cube. So from this we get x cube as minus 3 minus 24, which is minus 27. This is minus 27 is nothing but minus 3 the whole cube. So we get x cube is equal to minus 3 the whole cube. Therefore x is equal to minus 3. So the value of x is minus 3. And next we have the next term, which is minor of an element. In a given determinant, minor of an element Aij, it is the determinant which is obtained by deleting the ith row and the jth column in which Aij lies, and it is denoted by Mij. So we get the minor of an element Aij by deleting the ith row and the jth column. So here find the minor of element 7 in this determinant B equal to this determinant. So we have to find the minor of this element. So it is the determinant obtained by deleting 7 is in the second row and third column. So we have to delete the second row and third column and we have to find the determinant. So it is minor of M23. It is determinant of 2, 3, 1, minus 2. This is minus 4 minus 3, which is minus 7. So this is the determinant of this element 7. And next we have cofactor of an element of a determinant. In a square matrix, cofactor of an element Aij which is denoted by capital Aij or Cij. It is defined by Aij equal to minus 1 the whole raised to I plus j Mij, where Mij is the minor of the element Aij. So this is cofactor of an element of a determinant. So in the previous example, if we want to find the cofactor of this element A23, it is nothing but it is minus 1 the whole raised to 2 by 2 plus 3 into the minor of that element. So minus 1 the whole raised to 5 is, it is minus 1 into minus 7. So this is 7. So this is the cofactor of element 7. And next we can find the determinant of a matrix of order 3 using the cofactors. So here, if you want to find the determinant of a square matrix of order 3, which is given by this determinant, we can find this as A11 into cofactor of this element, which is given by capital A11 plus A12 into cofactor of A12 plus A13 into cofactor of A13. So this is how we can find the value of this determinant of a square matrix of order 3. If the determinant of any matrix is 0, then that matrix is called a singular matrix. And next we have one property with respect to cofactors. When the elements of a row or column of a determinant, if it is multiplied with cofactors of any other row or column, then their sum is always 0. Say for example, if the elements of first row, if it is multiplied by the cofactors of third row, that is if we have A11 into capital A31 plus A12 into cofactor of A32 plus A13 into cofactor of A33, then this will be equal to 0. The value of this will be 0. Similar question was asked in last year's sample question paper. In a 3 by 3 matrix A, value of A12 C13 plus A22 C23 plus A32 C33, where Cij is the cofactor of Aij is. So here if we have a matrix of the form A11, A12, A13, then A21, A22, A23, A31, A32, A33. Here we can see that A12, A22, A32, all these are elements of the second column. And C13, C23, C33, they are the cofactors of the elements of third column. So if we have the sum of product of elements of one column with the cofactors of elements of another column, then the sum of this, it will be equal to 0 because of the property that we just now saw. This is the property that we just now saw. Because of this, the value of this is equal to 0. Next we have the next question. Find minors and cofactors of the elements of this determinant and check whether A11 A31 plus A12 A32 plus A13 A33, it is equal to 0. So here we have to check that property. So let us find the minors and cofactors of each of the element in this determinant. So M11 is the value of the determinant which is obtained by deleting the first row on the first column. So it is 0 minus 20, which is minus 20. And then the cofactor is minus 1 the whole raised to 1 plus 1, which is 2, into M11 minus 20. So it is minus 20. And next we have M12. M12 is the determinant obtained by deleting the first row on the second column. So it is this determinant 6, 4, 1, minus 7. So the value is minus 42 minus 4, so it is minus 46. And then the cofactor is minus 1 the whole cube into minus 46, so it is 46. Then we have M13. It is the value of the determinant obtained by deleting the first row and the third column. So it is 6, 0, 1, 5. So it is 30 minus 0, which is 30. Then A13. It is minus 1 the whole raised to 1 plus 3, 4 into the minor, which is 30. So this is 30. And next we have M21. It is obtained, the determinant obtained by deleting the second row and the first column. So it is minus 3, 5, 5 minus 7. So this is 21 minus 25, which is minus 4. The cofactor is minus 1 the whole cube into the minor, which is minus 4. So it is minus of minus 4 plus 4. Next we have M22. It is the value of the determinant obtained by deleting the second row and the second column. So it is minus 14 minus 5 minus 19. A22 will be minus 1 the whole raised to 4 into minus 19, which is minus 19. And next we have the minor of the element A23. So M23 it is obtained by deleting the second row and the third column. So the determinant is 2 minus 3, 1, 5. So this is 10 plus 3, which is 13. And next we have the cofactor A23. It is nothing but minus 1 the whole raised to 2 plus 3, which is 5 into M23. So it is minus 1 into 13, which is minus 13. Next we have M31. It is the determinant obtained by deleting the third row and the first column. So it is minus 3, 5, 0, 4. This is minus 12. And the cofactor is minus 1 the whole raised to 3 plus 1, which is 4 into M31. So it is minus 12. Next we have M32. It is the determinant obtained by deleting third row and the second column. So it is 2, 5, 6, 4. This is 8 minus 30, which is minus 22. The cofactor is A32. It is minus 1 the whole raised to 5 into the minor. So it is minus 1 into minus 22, which is plus 22. And next we have M33. Determinant obtained by deleting third row and third column. So it is determinant of 2 minus 3, 6, 0. This is 0 plus 18, which is 18. And the cofactor is A33 is minus 1 the whole raised to 6 into the minor, which is 18. So this is equal to 18. Now we have to check whether this is equal to 0. A11 into A31 plus A12 into A32 plus A13 into A33. This is equal to A11, A12, A13 are the elements in the first row. So it is 2 into A31, A31, A32, A33 are the cofactors of the elements of third row. So A31 is minus 12 plus A12 is minus 3 into A32 is 22 plus A13 is 5 into A33 is 18. So this is equal to minus 24 minus 66 plus 90. So this is minus 90 plus 90, which is 0. So the value of this is equal to 0. Moving on. Next question. Find K if A equal to minus 2, 3, K, 4. It is a singular matrix. So here we have to find the value of K if K is a singular matrix. So we saw that a matrix is a singular matrix if the determinant value is equal to 0. So here A is singular, implies determinant of A equal to 0, which means determinant of minus 2, 3, k, 4, this is equal to 0. So the value of the determinant is minus 8, minus 3k equal to 0. From this we get minus 8 equal to 3k. Therefore, k equal to minus 8 by 3. So this is the value of k. Next we have adjoint of a matrix. The adjoint of a square matrix A, it is nothing but it is the transpose of the cofactors of A. So the transpose of cofactors of a matrix of square matrix A, it is called the adjoint of A. Next we have the properties of adjoint of a matrix. So for any given square matrix A of order n, A into adjoint A equal to adjoint A into A, it is equal to determinant of A into I. So this is the value for A into adjoint of A, and it is equal to adjoint of A into A. And then determinant of adjoint of A, it is equal to determinant of A the whole raised to n minus 1, where n is the order of the matrix. Next we have the formula of area of triangle using determinants. So if we have a triangle ABC with vertices x1, y1, x2, y2 and x3, y3, then the area of this triangle is given by this formula, half of determinant x1, y1, 1, x2, y2, 1, x3, y3, 1. So here if we get a negative value here, we can take the absolute value of the determinant since area is a positive quantity. Then if the area is given, then we have to use both positive and negative values of the determinant for calculation. If this value is equal to 0, then the meaning is that A, B and C are collinear. That is A, B and C lie on a straight line. So we say that if the area of the triangle is 0, then the 3 points A, B, C, they lie on a straight line. They are collinear. Now we have an example for what value of k? Points P3, 2, Q8, 8 and RK, 2 are collinear. So here we say these 3 points are collinear when the area of the triangle is 0. So we can find the area of the triangle using the determinant formula. Area of PQR, it is given by half of determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1 equal to 0. Only then these 3 points will be collinear. This implies half of 3 minus 2, 1, 8, 8, 1, k, 2, 1. This determinant, it is equal to 0. So here we have half into this determinant equal to 0 means we can consider this determinant alone as equal to 0 and we can expand along R1. Expanding along R1. 3 into 8 minus 2, minus of minus 2 plus 2 into 8 minus k plus 1 into 16 minus 8k equal to 0. So from this we get 18 plus 16 minus 2k plus 16 minus 8k equal to 0. So this is 50 minus 10k equal to 0 or 10k equal to 50, k equal to 5. Therefore, the condition for the value of k so that these 3 points are collinear is that k should be equal to 5. Now we'll see the properties of determinant. For any two square matrices A and B, then the multiplication of the determinant values is same as the determinant of their product. That is, determinant of A into B, it is equal to determinant of A into determinant of B. We saw this in one of the examples. If two square matrices A and B of order n are such that A is equal to K into B, then determinant of A equal to K raised to n into determinant of B, where n is 1, 2, 3, etc. Then the value of the determinant, it remains unchanged if the rows and columns are interchanged. The next property is if any two rows or if any two columns of the determinants are interchanged, then the sign of the determinant will change. Next property is if any two rows or any two columns of a determinant are identical, then the value of the determinant is 0. Next we have the next property. If corresponding elements of any two rows or any two columns are in the same ratio, then the value of the determinant is 0. Say for example, if we have this determinant, here we can see that the ratio of C1 to C3 is 1:2. So the value of this determinant, if you expand along any row or any column, the value will be equal to 0. If all elements in any one row or any one column of the determinant is 0, then the value of the determinant is 0. So here if we can see that the elements of the second column is 0. If we expand this determinant along C2, then we will get the value of the determinant as equal to 0. Here again, if we consider another determinant, here the first row is 0, the value of this will be 0. Next property is if sum or all elements of a row or column of a determinant is expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. Let us continue with the property. The next is if each element of a row or a column, if it is multiplied by a non-zero constant k, then the determinant value will get multiplied by k. Then the next property is if a row Ri is added to equimultiples of corresponding elements of another row Rj, then the value of the determinant remains the same. That is, if we perform the operation Ri changing to Ra plus k into Rj, or if we perform the operation Ci changing to Ci plus k into Cj, where k is any non-zero scalar, then the value of the determinant will not change. We usually use this property to simplify a determinant. And then if elements of a row or column are multiplied with cofactors of any other row or column, then their sum is 0. This property we have already seen. Next we have the examples on finding the value of determinant, where we have to use the properties of determinant and find the value. Evaluate determinant of this. So here let us use the properties of determinant. So here let us apply the operation applying C1 changing to C1 minus 8 C3. We get delta as 42 minus 40 is 2, 79 minus 72 is 7, then 29 minus 24 is 5. The other columns remain the same. So here the value of this determinant is equal to 0 since C1 is equal to C2. Next question, evaluate the value of this determinant. So here applying C3 changing to C3 plus C2, we get delta as 1, 1, 1, A, B, C, then A plus B plus C, A plus B plus C, A plus B plus C. Again the value of this determinant is also equal to 0 since C1 by C3 is in the ratio 1:A plus B plus C. Next question, given that A, B, C are in arithmetic progression, evaluate delta is equal to this determinant. So here it is given A, B and C are in arithmetic progression. So if A, B, C are in arithmetic progression, we can write 2B equal to A plus C. So here applying R1 changing to R1 plus R3 minus 2R2. So it becomes, so here it will be 6y plus 10 minus 6y minus 10, and then here then 12y plus 16 minus 12y minus 16, then here 18y plus A plus C minus 18y minus 2b. The remaining rows will remain the same. So here this will be 0. This will also be 0. Here we will have A plus C minus 2b. A plus C minus 2b. A plus C, this is A plus C. A plus C minus 2b is again 0. So this reduces to 0, 0, 0. 3y plus 5, 6y plus 8, 9y plus b, 4y plus 6, 7y plus 10, 10y plus c. So the value of this is 0 since one entire row is 0. Moving on to the next question. Without expanding, we have to prove that the value of this determinant is given by this expression xyz into x minus y, y minus z, z minus x. So here if you see this determinant, in this first column x is common, in this second column y is common, and in this third column z is common. So let us take those outside. Taking x from C1, y from C2 and z common from C3. We get delta equal to xyz into 1x x square, 1y y square, 1z z square. And next, let us apply C1 changing to C1 minus C2 and C2 changing to C2 minus C3. We get delta as xyz into C1 changing to C1 minus C2, 0, x minus y, x square minus y square. Here 0, y minus z, y square minus z square, 1z, z square. Again here we can see that x minus y is common here and y minus z is common here. That can be taken outside. Taking x minus y common from C1 and y minus z common from C2. We get xyz into x minus y into y minus z into 0, 1. This is x minus y into x plus y. We have taken x minus y outside, so we get x plus y. Here it is 0, 1. Similarly, here it is y plus z. And then here 1z, z square. And next let us apply the operation, applying C2 changing to C2 minus C1. We get delta equal to xyz into x minus y into y minus z into 0, 1 x plus y, and here 0, 0 z minus x, then 1 z, z square. So from here let us take z minus x common. Taking z minus x common from C2. So delta equal to xyz into x minus y, y minus z into z minus x into 0, 0, 1, 1, 0 z, x plus y, 1 z square. Now we can expand along R1. Expanding along R1, we get delta as xyz into x minus y, y minus z, z minus x. It will be 0 into which is 0, minus 0 into which is 0, plus 1 into 1 minus 0 which is 1 into 1. So this is equal to the right hand side. So this is what we have to do. And now we have the next example. Without expanding, evaluate this determinant. It is determinant of b plus c the whole square, a square, b square, c plus a the whole square, b square, then c square, a plus b the whole square. And we have to check whether this is equal to 2 into abc into a plus b plus c the whole cube. So here let us use the properties of determinants and evaluate this determinant. So first let us applying C1 changing to C1 minus C3 and C2 changing to C2 minus C3. We get delta equal to b plus c the whole square minus a square, then b square minus b square will be 0, then c square minus a plus b the whole square. And here C2 changing to C2 minus C3, a square minus a square will be 0. And here we will have c plus a the whole square minus b square. And here c square minus a plus b the whole square. The third column remains the same. So here if we consider the first column and the second column, a plus b plus c is common, which can be taken outside. So taking a plus b plus c common from C1 and C2. So delta becomes a plus b plus c the whole square into, here if we take, this is of the form a square minus b square, so this is b plus c plus a into b plus c minus a. We have taken b plus c plus a here, so we are left with b plus c minus a, then 0. Here it is c minus a minus b into c plus a plus b. We already took c plus a plus b here, so this is c minus a minus b. Similarly, in the second column, here we have c plus a plus b, it is outside, into c plus a minus b. So here we have c plus a minus b. And here again we have c minus a minus b. C minus a minus b. And here a square, b square, a plus b the whole square. And after this, let us apply R3 changing to R3 minus R2 minus R1. So here applying R3 changing to R3 minus R2 minus R1. So delta becomes a plus b plus c the whole square into the first two rows remain the same, 0 a square, then 0 c plus a minus b square. R3 changes to R3 minus R2 minus R1. So here we will have c minus a minus b minus c plus a. So here minus c minus a will go. Here we will have minus 2b. And then here we will have c minus a minus b, then minus of this term, minus c minus a plus b. So c and c will get cancelled. Here we will have minus 2a. And here it will be a plus b the whole square, then minus a square minus b square. So it is a plus b the whole square is a square plus b square plus 2ab minus a square minus b square. So a square, b square will go. So here we will have 2ab. And now here 2 is common from the third row, which can be taken outside. Taking 2 common from R3. So we will get delta as 2 into a plus b plus c the whole square into determinant of b plus c minus a, 0 a square, then 0 c plus a minus b square, then minus b minus a and ab. So we have used the properties of determinants, and we have simplified the given determinant up to this step. Now we can expand along R1. Expanding along R1. So delta becomes 2 into a plus b plus c the whole square into b plus c minus a into, here it is c plus a minus b into ab. So it becomes abc plus a square b minus ab square and minus of ab square. So it is plus ab square. Plus ab square. Then we have minus 0 plus a square into 0. This is 0 into minus a is 0. Then plus b into c plus a minus b. So it is plus bc plus ab minus b square. So here minus ab square and plus ab square will get cancelled. Here we can see that ab is common, it can be taken outside, and here also ab is common, which can be taken outside. So delta equal to 2 into a plus b plus c the whole square into ab into b plus c minus a into c plus a. So here b is common, we can take it outside. We are trying to take ab outside, so we can write it as plus a into ab into, here we have c plus a minus b. So here ab is common, which can be taken outside. So this becomes 2ab into a plus b plus c the whole square. So here we have to multiply b plus c minus a into c plus a. We have taken ab common outside. So it is into bc plus c square minus ac plus ab plus ac minus a square. And here we have plus ac plus a square minus ab. So here minus ac plus ac will go, plus ab minus ab will go, minus a square plus a square will go. So we are left with bc plus c square plus ac. Here again c is common, which can be taken outside. So this is 2abc into a plus b plus c the whole square into b plus c plus a. This b plus c plus a is nothing but a plus b plus c. So this is equal to 2abc into a plus b plus c the whole square. So we are asked to evaluate this integral, and it is equal to 2abc into a plus b plus c the whole cube. It is a plus b plus c the whole square into a plus b plus c. So it is a plus b plus c the whole cube. So this is delta. Now we have the next example. Evaluate without expanding delta equal to determinant of 1 plus a 1 1, 1 1 plus b 1, 1 1, 1 plus c. So here let us applying C1 changing to C1 by A. That is, let us take A from the first column, B from the second column, and C from the third column outside, so that we will have delta equal to ABC into these operations. Then C2 changing to C2 by B and C3 changing to C3 by C. So we will get delta as ABC into, here if we take A outside from this column, we will get 1 by A plus 1, or it is 1 plus 1 by A, and here 1 by A, 1 by A. Here it will be 1 by B, then here it will be 1 by B plus 1, or it is 1 plus 1 by B, and here 1 by B. Here it is 1 by C, 1 by C. Here it will be 1 by C plus 1, which is 1 plus 1 by C. And now let us apply C1 changing to C1 plus C2 plus C3. Applying C1 changing to C1 plus C2 plus C3. So we get delta as ABC into, it will be 1 plus 1 by A plus 1 by C. Here also it will be 1 by A plus 1 by B plus 1 by C, which is 1 plus 1 by A plus 1 by B plus 1 by C, and here again 1 plus 1 by A plus 1 by B plus 1 by C. The other columns remain the same. And now we can see that this is common from the first column. So taking, let me continue here, taking 1 plus 1 by A plus 1 by B plus 1 by C common from C1. So delta becomes ABC into 1 plus 1 by A plus 1 by B plus 1 by C into determinant of first column becomes 1 1 1, then the other columns are as it is. 1 by B, 1 plus 1 by B, 1 by B, then 1 by C, 1 by C, and 1 plus 1 by C. And now let us perform R1 changing to R1 minus R3. So applying R1 changing to R1 minus R3, we get delta as ABC into 1 plus 1 by A plus 1 by B plus 1 by C. So the first term will be 1 minus 1 0, then here it will be 1 by B minus 1 by B 0, and here it will be 1 by C minus 1 by C, which is minus 1. So it becomes 0 0 minus 1, then 1 1 plus 1 by B 1 by C, then 1 1 by B 1 plus 1 by C. And now we can expand along R3. I'm sorry, R1. Expanding along R1. So we will have 0 into this term 0, again 0 into this 0, then minus 1 into, we will have 1 by B, minus 1 minus 1 by b. So we will be left with 1. Delta becomes ABC into 1 plus 1 by a plus 1 by b plus 1 by c into here 1 by b minus 1 minus 1 by b minus 1 into. So here we have minus 1 into minus 1, which is plus 1. So this is equal to ABC into 1 plus 1 by a plus 1 by b plus 1 by c. So the value of this determinant is equal to ABC into this expression. This is what we have. Now if we take LCM here, then we will get this is equal to ABC into, if we take LCM, we will have here ABC plus, LCM is ABC, so here we will have ABC plus BC plus AC plus AB. So ABC and ABC will get cancelled. So from this we will get delta as equal to ABC plus AB plus BC plus AC. So we have evaluated the value of this determinant using the properties of determinants. Now let us proceed. The next topic is inverse of a matrix. So if we have a square matrix A of order n, and if there exists another square matrix B of the same order n such that AB equal to BA equal to the identity matrix I, then we say A is invertible and B is called the inverse matrix of A, and it is denoted by A inverse. So if we consider A as this matrix 2, 1, minus 3, 5, and B as this matrix 5 by 13, minus 1 by 13, 3 by 13 and 2 by 13. Here we can see that A into B, when we multiply, we get it as the identity matrix. So this B, this is the inverse of A. Therefore, B equal to A inverse, which is equal to 5 by 13, minus 1 by 13, 3 by 13 and 2 by 13. So this is A inverse. Next we have the properties of inverse of a matrix. So inverse of a matrix, if it exists, it is unique. So there is only a single inverse for a given matrix. For two invertible matrices of same order, say A and B, then AB the whole inverse is equal to B inverse A inverse. Then for invertible matrix A inverse the whole inverse is equal to A, and A transpose the whole inverse is equal to A inverse the whole transpose. So these are the properties of inverse of a matrix. And next we have the method to find the inverse of a given square matrix. There are various methods available. One is the elementary operation or transformation method. The second one is matrix or adjugate or adjoint method. And the third one is row reduction method. So we are having only this matrix method, matrix or adjugate or adjoint method. So we will see how we can find the inverse of a matrix by coefficient matrix method. So we know that this property A into adjoint of A, it is equal to adjoint of A into A equal to determinant of A into I, where I is the identity matrix of order n. So from this we can find the inverse of A by A inverse will be 1 by determinant of A into adjoint of A. So here if we consider A into adjoint of A equal to determinant of A. Now let us pre-multiply both sides by A inverse. So A inverse A adjoint of A equal to A inverse into determinant of A. So here A inverse A will be equal to I. This is I. So from this we get A inverse equal to 1 by determinant of A into adjoint of A. So here only when the determinant of A is not equal to 0, we can find the inverse of A. So only a non-singular square matrix is invertible. If determinant of A equal to 0, then we call such a square matrix as a singular matrix only when determinant of A is not equal to 0. That is, only when a square matrix is non-singular, then we can find the inverse of the matrix, or we say it is invertible. And now let us find the inverse of this matrix A using inverse of the coefficient matrix method. Find the inverse of A using inverse of coefficient matrix method when A equal to 2, 3, 10, 4, minus 6, 5, 6, 9 and minus 20. So here first let us find determinant of A and check whether the matrix is singular or non-singular. Determinant, or first let us write the formula. A inverse equal to 1 by determinant of A into adjoint of A. Adjoint of A is nothing but we have studied it is the transpose of the cofactor matrix of A. Determinant of A equal to determinant of 2, 3, 10, 4, minus 6, 5, 6, 9, minus 20. So this is equal to 2 into 120 minus 45 minus 3 into minus 80 minus 30 plus 10 into 36 minus of minus plus 36. So this, when we simplify, we get it as 150 plus 330 plus 720. This is equal to 1200. This is not equal to 0. So we can find inverse of A. And now let us find adjoint of A. Adjoint of A, it is the transpose of the cofactor matrix. So let us first find the cofactor matrix and then find the transpose. So cofactor of this first element, it is the determinant of minus 6, 5, 9, minus 20 into minus 1 the whole square. So it is positive. So cofactor of 2 is 120 minus 45. Then here we have a negative symbol. So the cofactor of this element is, we have to delete first row on the second column. So it is minus of minus 80 minus 30. And then here it is 36 plus 36. Next we have the cofactor of the element in the second row first column. So it is minus 60 minus 90. And then we have minus 40 minus 60. And then it is 18 minus 18 with a negative sign. And next we have the cofactor of this element, that is the element in the third row first column. So here it is positive 15 plus 60, and here it is negative 10 minus 40. Here again it is positive, so minus 12 minus 12. The whole transpose. So here it is 120 minus 45, 75. Here it is minus of minus 110 plus 110. This is 72. And here it is minus of minus 150 plus 150. Then minus 100, 0. Then 15 plus 60, 75. Minus of minus 30 plus 30 and minus 24. The whole transpose. So this is equal to, the transpose of this is 75. Rows become columns. 150 minus 100, 0. Then 75, 30 and minus 24. So A inverse is 1 by determinant of A into adjoint of A. So A inverse is 1 by 1200 into adjoint of A. 75, 150, 75, 110 minus 130, 72, 0, minus 24. So here we can write it as fractions. 75 by 1200, 1 by 16. 150 by 1200, 1 by 8. Here again 1 by 16. This is 11 by 120. This is minus 1 by 12. And it is 1 by 40. Then 72 by 1200, 3 by 50. 0. Minus 24 by 1200. Minus 1 by 50. So this is A inverse. So this is how we have to find the inverse of a matrix, given matrix, using coefficient matrix method. Now we'll move on to the last topic, which is solving a system of simultaneous linear equations. Under solving system of simultaneous linear equations, we have two methods. The first one is inverse of coefficient matrix method and the other one is Cramer's rule. So in inverse of coefficient matrix method, here this method is used to solve a system of equations in two or more variables. So we can write the given system of equations in the matrix form. So if we have the system of equation of this form, 2x minus 3y equal to 5, 5x plus 3y equal to 2, we can write this in the matrix form as Ax equal to b. Now if we pre-multiply both sides by A inverse, we will get I into x is equal to A inverse into b, or x is equal to A inverse into b. So by finding A inverse and after multiplying it with b, we can find the values of x and y. And now let us solve a question using this method. Solve the following system of equation finding the inverse of coefficient matrix. So we have x minus y equal to 5, 2x plus 3y equal to minus 1. We have to solve these two equations using inverse of coefficient matrix method. So we can write the given system of equations. It can be written in the matrix form as Ax equal to b, where A is the coefficient matrix, where A is the matrix 1, minus 1, 2, 3. Then x is the variable matrix x, y, and b is the constant matrix 5, 1, minus 1. Now we have Ax equal to b implies x equal to A inverse into b. So we have to find A inverse. Now before finding A inverse, we have to check whether A is singular or non-singular. For that we have to find the determinant of A. Determinant of A is 3 plus 2, which is 5, not equal to 0. So we can find A inverse since determinant of A is not equal to 0. And then we need to have adjoint of A. So if the matrix is a 2 by 2 matrix, then the adjoint of A is obtained by interchanging the diagonal elements and changing the sign of the other elements. So here we can interchange the diagonal elements and we can change the sign of the other elements. So this is adjoint of A only when it is a 2 by 2 matrix. So A inverse equal to 1 by determinant of A into adjoint of A. So this is 1 by 5 into adjoint of A is 3, 1, minus 2, 1. Let us take this as 1. From 1, x equal to A inverse B implies the variable matrix x comma y. This is equal to A inverse is 1 by 5 into 3, 1, minus 2, 1 into B. B is the constant matrix 5, 1, minus 1. So this is 1 by 5 into 15 minus 1, 14, and the second element is minus 10 minus 1, minus 11. So this is 14 by 5 and minus 11 by 5. So we got this matrix x and y as 14 by 5 and minus 11 by 5. Therefore, x equal to 14 by 5 and y equal to minus 11 by 5. So this is the solution for the given system of linear equations. Now we'll see the next example. Solve the following system of equation using matrix method. So here we have three linear equations in three unknowns x, y and z. Similar question was asked in the sample paper for 5 marks. So here the given system of equations, it can be written in the matrix form as Ax equal to B, where A equal to the coefficient matrix 1, 1, 1, 2, 1, 0, 1, 1, minus 4. Then x equal to the variable matrix x, y, z, and B is the constant matrix 10, 13, 0. So Ax equal to B implies x is equal to A inverse into B. Let us take this as 1. Now we have to find A inverse. We have A inverse equal to 1 by determinant of A into adjoint of A. So let us find determinant of A. Determinant of A, we can expand along R1. Determinant of A is 1 into minus 4 minus 1 into minus 8 minus 0 plus 1 into 2 minus 1, 1. So it is 8 minus 4 plus 1, which is 5. So this is equal to 5, not equal to 0. Therefore, A inverse exists. And now let us find adjoint of A. Adjoint of A, it is the transpose of the cofactor matrix of A. So here cofactor of this first element, it is minus 4. Then cofactor of this element, it is minus of minus 8 minus 0. And then the cofactor of this element is 2 minus 1, 1. Next we have the cofactor of this element 2. It is minus of minus 4 minus 1 minus 5. Then the next element is cofactor of this element A22. It is minus 4 minus 1 minus 5. Here we have a negative sign. Cofactor of this element 0. It is 1 minus 1, 0. Next we have cofactor of this element. It is 0 minus 1 minus 1. Next we have a negative sign. It is 0 minus 2. Minus 2. Next we have the cofactor of this last element. So it is 1 minus 2 minus 1. The whole transpose. So this is minus 4, 8, 1, 5, minus 5, 0, minus 1, 2, minus 1 transpose. So adjoint of A is minus 4, 8, 1, 5, minus 5, 0, minus 1, 2, minus 1. So this is adjoint of A. So A inverse is 1 by determinant of A into adjoint of A. Therefore, A inverse equal to 1 by determinant of A into adjoint of A. It is equal to 1 by 5 into minus 4, 5, minus 1, 8, minus 5, 2, 1, 0, minus 1. And now we have x is equal to A inverse into B. So x is equal to 1 by 5 into minus 4, 5, minus 1, 8, minus 5, 2, 1, 0, minus 1 into B. B is 10, 13, 0. So this x is nothing but it is the variable matrix x, y, z. So this is equal to 1 by 5 into, here it is minus 40 plus 65, which is 25, and here it is 8 into 10, 80, minus 5 into 13, 65, which is 15, and here it is 1 into 10 plus 0 plus 0, so it is only 10. So this is equal to 5, 3, 2. So we got the variable matrix x, y, z as 5, 3, 2, which means x is equal to 5, y is equal to 3, and z is equal to 2. So here a similar question was given in the sample paper for 5 marks. Here finding A inverse up to this step carries 2 marks, and then finding the values for x, y, and z and writing it separately. The remaining part carries 3 marks. So a total of 5 marks. Next we have solving a system of simultaneous linear equations using Cramer's rule. So let us take, let the given system of linear equations be a1x plus b1y equal to c1, a2x plus b2y equal to c. So here when we have this given system of linear equations, we can have the determinant delta as determinant of the coefficient matrix, which is a1, b1, a2, b2, and delta x is the determinant which is obtained by removing a1, a2 and substituting the constants c1, c2. So here delta x is determinant of c1, b1, c2, b2, and delta y is the determinant which is obtained by removing the coefficients of y and putting the constants there. So it is a1, c1, a2, c2. Now using this Cramer's rule, we can find the value of x as delta x upon delta and y as delta y upon delta. So this is a very easy method to find the solution of given system of linear equations. So this is when we have a system of two linear equations in two unknowns. So if we have a system of linear equations in three unknowns, then we have the determinant of the coefficient matrix which is given by delta. So this is delta. Then we have delta x which is obtained by removing the coefficient of x terms and replacing it with the constant terms given in the equation. So delta s is x is determinant of this, and next we have delta y as the determinant of a1, a2, a3, and here we have to remove the coefficients of y and replace it with the constant terms here. So it is a1, a2, a3, d1, d2, d3, c1, c2, c3, and finally delta z is obtained by this determinant where we replace the coefficient of z terms in delta by the constant terms. So this is delta z, determinants of a1, a2, a3, b1, b2, b3, d1, d2, d3. So from this we find x as delta x upon delta, y as delta y upon delta, and z as delta z upon delta. So this is how we can use Cramer's rule when we have a system of linear equations in three unknowns. Now we will see the condition that has to be satisfied for various types of equations. So if we have a given system of equations of this form, a1x plus b1y equal to 0 and a2x plus b2y equal to 0. Here the elements of the constant matrix is 0. Then we have such a system of equations, it is called homogeneous equations. And then in Cramer's rule, if we have delta not equal to 0, then the given system of equations, it is consistent and it has a unique solution. So here we can obtain the value of x, y and z using this relation. In all these places, it is in the denominator. Delta is in the denominator. If this is not equal to 0, then we call the given system of equations as consistent and it will have a unique solution. Now let us solve this problem. Solve the following system of equations using Cramer's rule. So we have 2x minus 3y equal to 5 and 5x plus 3y equal to 2. So the given system of equations can be written in the matrix form as Ax equal to B. That is 2 minus 3, 5, 3 into xy equal to B, 5, 2. Now let us find delta, delta x and delta y. Now delta is determinant of 2 minus 3, 5, 3. So it is 6 plus 15 which is 21. So delta x is, we have to remove this 2 and 5 and substitute the constants 5 and 2. So it is determinant of 5, 2 minus 3, 3. So this is 15 plus 6 which is again 21. Next we have delta y. Delta y, it is, you have to remove the coefficient of y terms and substitute the constants. So it is 2, 5, 5, 2. So this is 4 minus 25 which is minus 21. So from here we have x as delta x upon delta. So it is 21 by 1 which is 1. And y as delta y upon delta which is 21 by minus 21 minus 1. Therefore we get x as 1 and y as minus 1. So here we can see that this delta, this is not equal to 0. So here the system of equations is consistent and it has a unique solution. Now let us move on to the next question. Solve the following system of equations using Cramer's rule. So here we have 3 equations in 3 unknowns. So the given system of equations can be written in the matrix form as Ax equal to B. That is 1, 1, that is the constant matrix, 2, 1, 0, then 1, 1, minus 4 into x is the variable matrix x, y, z equal to B, which is the constant matrix. Now let us find delta, delta x, delta y and delta z. Now delta equal to determinant of 1, 1, 1, 2, 1, 0, 1, 1, minus 4. So let us expand along R1. So it is 1 into minus 4, minus 1 into minus 8, plus 1 into 2 minus 1, 1. So this is 8 minus 4, 4, plus 1, 5. So delta is 5. This is not equal to 0. Hence the given system of equations is consistent and it has a unique solution. Delta x will be, we have to replace the first column with the constants. 10, 13, 0, 1, 1, 1, 1, 0, minus 4. Again let us expand along R1. So it is 10 into minus 4 minus 0, minus 1 into minus 52 minus 0, plus 1 into 13 minus 0. So this is 52 minus 40 which is 12 plus 13, 25. Next we have delta y. Delta y, the first column will remain the same. The second column we have the constants. And third column remains the same. So again expanding along R1. So it is 1 into minus 52 minus 0, then minus 10 into minus 8 minus 0, then plus 1 into 0 minus 13. So this is 80 minus 65 which is 15. Next we have delta z. For finding delta z, the first two columns will remain the same. The third column should be replaced with the constants. So delta z is determinant of 1, 2, 1, 1, 1, 1, 10, 13, 0. So again we can expand along R1. So it is 1 into 0 minus 13 minus 13, then minus into 0 minus 13 minus 13, then plus 10 into 2 minus 1 is 1. So this is minus 13 plus 13 plus 10. So it is equal to 10. Now delta x is, x is delta x upon delta. So it is 25 by 5, which is 5. Y is delta y by delta. It is 15 by 5, which is 3. And z is delta z by delta. It is 10 by 5, which is 2. Therefore, x equal to 5, y equal to 3, and z equal to 2. So this is the solution for the given system of equations which we have found using Cramer's rule. Now moving on to the next condition. In Cramer's rule, when delta equal to 0 and all other delta values, delta x, delta y and delta z are 0, then the system of equations is dependable consistent and it has infinitely many solutions. So if we have a situation like this, when delta equal to 0 and all these are also equal to 0, then we call the system of equations as dependable consistent and it has infinitely many solutions. Now let us see a problem. Solve the following system of equations using Cramer's rule. So here the given system of equations can be written in the matrix form as Ax equal to B. So here A is the coefficient matrix 2, minus 3, minus 4, 6. X is the variable matrix xy and B is the constant matrix. Now let us find delta, delta x and delta y. So delta equal to determinant of 2, minus 3, minus 4, 6. So this is 12 minus 12, which is 0. So we are getting delta as 0. Now let us see what we get for delta x and delta y. Delta x is determinant of 5 minus 10 minus 3 is 6. So this is 30 minus 30, which is again 0. And delta y is, it is 2 minus 4, 5 minus 10. So this is minus 20 plus 20, which is again 0. So we get delta equal to 0, delta x equal to 0 and delta y equal to 0. So here we just now saw if delta equal to 0 and delta x and delta y are all 0, then the given system of equations is dependable consistent and we have infinitely many solutions. So the given system of equation has infinitely many solutions. So this is what we have just now seen. Next we have the next condition. In Cramer's rule, when delta equal to 0 and any one or more of the deltas, delta x, delta y and delta z are non-zero, then the system of equations is inconsistent and has no solution. So here if delta is 0 and if any of these values, if it is not 0, because we are getting x as delta x upon delta. If this is non-zero and if this is equal to 0, then obviously the system will have no solution. Next we have the next question. Solve the system of equations using Cramer's rule. So we have three equations in three unknowns. The given system of equations can be written in the matrix form as Ax equal to B. That is 1 minus 2, 3, 2, 1 minus 1, 3 minus 1, 2 into x, y, z equal to 1, 3 minus 2. Now let us find delta. So delta is determinant of 1 minus 2, 3 2, 1, minus 1, 3, minus 1, 2. So expanding along R1. So this is 1 into 2 minus 1, 1. Minus of minus 2 is plus 2 into 4 minus of minus 3 plus 3. Then plus 3 into minus 2 minus 3 minus 5. So this is 15 minus 15, which is 0. So we are getting delta as equal to 0. Now let us find delta x. Delta x is determinant of 1, 3, minus 2, minus 2, 1, minus 1, 3, minus 1, 2. Here we have to replace the first column with the constants. So again expanding along R1, we get 1 into 2 minus 1, 1, plus 2 into 6 minus 2, 4, plus 3 into minus 3 plus 2, minus 1. So this is 9 minus 3 is 6, which is not equal to 0. So here itself we can see that the given system of equation will not have a solution. It is inconsistent. Let us proceed with finding delta y and delta z. So delta y is 1, 2, 3, then 1, 3, minus 2, 3, minus 1, 2. So this is 1 into 6 minus 2, 4, minus 1 into 4 plus 3, 7, plus 3 into minus 4 minus 9, minus 13. So this is 4 minus 7 minus 39, it is minus 42, which is 0. Then delta z is, first two columns remain the same. The third column will have the constant. So this is 1 into minus 2 plus 3 is 1, plus 2 into minus 4 minus 9 minus 13, plus 1 into minus 2 minus 3 minus 5. So this is 1 minus 26 minus 5, it is minus 30, not equal to 0. So hence in Cramer's rule, when delta is 0 and any one or more of the deltas are non-zero, then the given system of equations is inconsistent and has no solution. So in this case, the given system of equation is inconsistent and has no solution. And here we have some word problems on matrices. Three shopkeepers A, B and C are using polythene bags, handmade bags and newspaper bags. A uses 20, 30 and 40 number of bags of respective type. Then B uses 30, 40 and 20 of each respective kind, while C uses 40, 20 and 30 of each type. Each shopkeeper spend rupees 250, rupees 220 and rupees 200 on the bags. Find the cost of each carry bag using matrix method. So here we are having three shopkeepers A, B and C who are using these three kinds of bags, and the number of each types of bags each shopkeeper uses, it is given here. And they have also given the amount that each shopkeeper spent on the bags. Now we need to find the cost of each carry bag using matrix method. So let us draw a table like this. So let us take the cost per bag as X, Y and Z. So here we have three shopkeepers A, B and C. A uses 20 polythene, 30, 40 and total cost spent is 250. Then B uses 30, 40, 20 and the amount spent is 220. C uses 40, 20, 30 and the amount spent is 200. So let us take the cost of one polythene bag as X, one handmade bag as Y and one newspaper bag as Z. So we can write this in the form of three equations given by 20x plus 30y plus 40z equal to 250. Then 30x plus 40y plus 20z equal to 220. And next we have 40x plus 20y plus 30z equal to 200. So we have to solve these three equations in x, y and z. So here we can simplify this further. So let us simplify it here. So we get the three equations as 2x plus 3y plus 4z equal to 25. Then 3x plus 4y plus 2z equal to 22. Then 4x plus 2y plus 3z equal to 20. So now we can represent these equations in the matrix form. The equations can be represented in matrix form as Ax equal to B, where A is the coefficient matrix 2, 3, 4, 3, 4, 2, 4, 2, 3. X is the variable matrix x, y, z, and B is the constant 25, 22, 20. So from this we can find x as A inverse into B. So for that first we have to find A inverse. So we have to check whether A is singular or not. Now determinant of A, let us expand along R1. It is 2 into 12 minus 4, which is 8, minus 3 into 9 minus 8, which is 1, plus 4 into 6 minus 16, which is minus 10. So this is minus 27, which is not equal to 0. So A inverse exists. Therefore, A inverse exists. Now let us find adjoint of A. So adjoint of A, it is the transpose of the cofactor matrix. So let us find the transpose of this cofactor matrix A. So A, the first element is positive. It is 12 minus 4, which is 8. Then here it is negative. 9 minus 8 is 1. So minus 1. And next we have 6 minus 16, which is minus 10. Then for the next term, it is negative. 9 minus 8 is 1. Next is positive. It is 6 minus 16 minus 10. Next it is negative. 4 minus 7. 4 minus 12. It is minus 8. So minus of minus 8 plus 8. And then for the next term it is 6 minus 16 minus 10. Next term it is negative. 4 minus 12 minus 8. Minus of minus 8 is plus 8. And next we have 8 minus 9, which is minus 1. Transpose. So this is 8 minus 1 minus 10. The transpose of this matrix, the rows become the columns. So minus 1 minus 10, 8, minus 10, 8, minus 1. We have A inverse equal to 1 by determinant of A into adjoint of A. We already found determinant of A, it is negative 27. So this is minus 1 by 27 into adjoint of A. It is this matrix 8 minus 1 minus 10, minus 1 minus 10, 8, minus 10, 8, minus 1. And now we have Ax equal to B. This implies x is equal to A inverse into B. So we can find x as A inverse, it is minus 1 by 27 into 8 minus 1 minus 10 minus 1 minus 10 8 minus 10 8 minus 1 into B, which is the constant matrix. It is 25 22 20. So this is equal to, here it is 18 to 25 200 minus 22 minus 200, and next we have minus 25 minus 220 plus 160, and next we have minus 260 plus 176 minus 20. So this x is nothing but it is the variable matrix x, y, z. This is minus 1 by 27 into this matrix. So it is minus 1 by 27 into, here we have minus 22, then minus 85, and then it is minus 94. So this is nothing but 22 by 27, 85 by 27 and 94 by 27. So from this we get x as, so we have taken x, y and z as cost of polythene bag, handmade bag and newspaper bag. So we got the values of x, y and z. So x is equal to rupees 22 by 27, y equal to rupees 85 by 27 and z is equal to rupees 94 by 27. So these are the values of x, y and z. Moving on to the last example, a school plans to award rupees 6,000 in total to its students to reward for certain values: honesty, regularity and hard work. When 3 times the award money for hard work is added to the award money for honesty, amounts to rupees 11,000. The award money for honesty and hard work together is double the award money for regularity. Use matrix method to find the prize money for each category of award. So here we have a school which plans to reward rupees 6,000 in total for 3 things. One is honesty, regularity and the other one is hard work, and they have some conditions which are given. So let us take, let rupees x, rupees y and rupees z be the prize money for honesty, regularity and hard work respectively. So here it is given a total of rupees 6,000 will be awarded for these 3 things. As a result we have x plus y plus z is equal to 6,000, and then it is given 3 times award money for hard work is added to award money for honesty. So 3 times the award money for hard work if it is added to award money for honesty, x plus 3z, this is equal to 11,000. And then it is given award money for honesty and hard work. So honesty and hard work, x plus z, x plus z. It is together double the award money for regularity. This is equal to 2y. Or we have x minus 2y plus z equal to 0. So we have to solve these 3 equations and find the values of x and y using matrix method. So here the given equations can be written in matrix form as ax plus b, where A is the coefficient matrix 1 1 1 1 0 3 1 minus 2 1. Then x is the variable matrix x y z, and b is the constant matrix 6,000 11,000 0. So now we have to find A inverse. For that, first we have to find determinant of A. So determinant of A, if we expand along the first row, it is 1 into 0 minus of minus 6 plus 6 minus 1 into 1 minus 3 minus 2 plus 1 into minus 2. So this is 6 plus 2, 8 minus 2, 6, which is not equal to 0. Hence A inverse exists. And next we have to find adjoint of A. Adjoint of A is the transpose of the cofactor matrix. So it is transpose of 6 plus 2 minus 2 minus 3 0 minus of minus 3 plus 3 then 3 minus 2 minus 1, the whole transpose. So if we take the transpose, the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. So we have A inverse as 1 by determinant of A into adjoint of A. So it is 1 by 6 into 6 minus 3, 3, 2, 0 minus 2, minus 2, 3, minus 1. Now Ax equal to B implies x equal to A inverse into B. So this implies x is equal to 1 by 6 into 6 minus 3, 3, 2, 0 minus 2, minus 2, 3, minus 1 into B. 6,000, 11,000, 0. So this is 1 by 6 into 36,000 minus 33,000, 3,000, then 12,000, then 33,000 minus 12,000, it is 21,000. So when we divide each term by 6, we get x is xyz, we get 500, 3,000 by 6, 500, 12,000 by 6, 2,000, 21,000 by 6, 3,500. Therefore, the price money for honesty is rupees 500, for regularity is rupees 2,000, and for hard work it is 3,500. So price money for honesty is rupees 500, regularity is rupees 2,000, and hard work is rupees 3,500. So this is the price money for each of these values. I hope this video was useful for you. If you have not subscribed to my channel, please subscribe. Thank you for watching.